You will match forms.
Yeah, I think I was last in this building 33 years ago, maybe a little bit more than that. So I said I would talk a little bit about computation, the future of mathematics. I guess that I have somewhat unwittingly over the years become probably the world's leading purveyor of ways that mathematics gets done at a practical level in the world, with two main things, Mathematica and Wolfram Alpha. Maybe I'll talk a little bit about those, and I'll also talk about the thing that was the reason I originally created Mathematica for myself, which was to have a mechanism for advancing various directions in science, which turn out in the end to have quite a bit to say about mathematics, I think. So perhaps I should, I suppose I should give the basic introduction to Wolfram Alpha here. The sort of the concept of Wolfram Alpha has been to try to take sort of the knowledge that exists in the world and as far as possible make it computable, in the sense that sort of the goal is if there's something that you could find an expert to answer, if you had a question which some expert could answer on the basis of knowledge that exists in the world, try and make it automatic to have that happen. And so, a type of question you might ask is, what's 2 plus 2? And hopefully this is a good way to check that everything is connected. This is a bad sign. It's not what's happening. I thought the network was working here. This is a very bad sign. I can always use Mathematica, which is purely local. Yes. Us humans can do that faster than this. Okay, let's see what's going on here. Oh dear. Well, 7 off. Okay, do I have to go back and type in? Okay. There I was thinking this had all been nicely debugged. Okay. Well, okay. What's that?
Looks like Wi-Fi is off, actually.
Wi-Fi should be off because it's connected to a wire here.
Well, no, on your laptop, if you click on the symbol and then you have to turn Wi-Fi on.
Yeah, but that's what I want is for Wi-Fi to be off, because it's supposed to be using. Well, okay. Oh dear. Okay. HCP should work. Dear. Okay, this was working just moments ago. Well, all right. I'll talk about. Let me talk about some things that don't require seeing Wolfram Alpha. How about that? It's a shame. We'll look at some things that do require seeing Wolfram Alpha later. Let's talk. Okay, maybe. Let me talk a little bit about a kind of direction in science that I've been interested in for a long time. That was sort of helped by.
I'm part of IT.
It's probably not going to work because if let's see.
No, without yeah. I mean, while you go on, I can.
I don't think it's a good idea because you don't know how to set up the. I think it's more likely to. Thank you though. Okay. Let's okay. About sort of directions in science. So one of the things so long ago I used to work on particle physics, and I got interested in questions about when I was in Oxford actually. I got interested in questions about how particle physics relates to things like cosmology and how the universe went from what appeared to be a sort of disorganized Big Bang state to the kind of complicated state that it's in today. And I was interested in how things like thermodynamics would or would not explain what was going on there. And that kind of led me eventually to the question of, well, how do complicated things get to happen in the world, in nature, and so on anyway? And if we look at sort of the history of science for the last few hundred years, kind of the biggest thing that happened was people realized about 300 years ago that you could use math to understand things about the natural world. And this was sort of the whole Newton, Galileo, etc. adventure that was very successful in letting one model all sorts of things about the natural world, like motion of planets, like electrodynamics, like all these kinds of things. But it was pretty clear, 30 years ago or something now, that while that had been very successful for lots of purposes, there were still lots of things in nature that we hadn't successfully explained using mathematics or using the methods that we had available. So I got interested in the question of, so how could we generalize what math had been so successful at doing in being able to model the natural world? What was the sort of more general category of thing that was like mathematics but allowed a sort of broader class of models and so on? And so what I realized at the time was that we did have a sort of a way of thinking about things more general than mathematics, and that had to do with things like computer programs. Because if you expect to make a model of something in nature or anywhere for that matter, the thing better be governed by some kind of definite rules. The question is, how should you represent those rules? Should those rules be represented by differential equations and exponentials and things like that? Or should they be represented by in some more general form? And so what one realized is that, well, we can use things like computer programs to represent sort of general rules for how things might behave. And so then that got me into the question of, okay, so let's say we imagine that we're going to use things like programs to represent the natural world. What kinds of programs might be relevant to that? Well, the programs, we're used to having programs that we specifically write for particular purposes, like, Wolfram Alpha is now 15 million lines of Mathematica code, and Mathematica is, I don't know, about 20 million lines of code itself. Those are big, complicated programs. But what might programs that nature is using to do what it does be like? So that got me into the sort of basic science question of, so what does the space of all possible programs look like? What happens if we sort of imagine enumerating programs, starting with sort of the simplest imaginable program, to see what they do? Well, so for example, let's see if we can make this work. Come on, something has to work here. Let me see. Oh, no, bad. 1 second. If this doesn't work, I'm really going to be upset. Okay. Well, I'm doing horribly here. No, that doesn't make much sense. Okay, I gotta make. I cannot describe this without pictures, so I have to make pictures work somehow. All right, let's see whether I can make this work. Not. Oh, that's a very bad sign. That's a very bad sign. And that is probably why. Okay, this is a combination of the network not working and, oh dear. Okay, just a minute. Let's see whether this will work now. Oh, come on. Oh. No, okay, better sign here. Okay, there we go. Okay, so anyway, so we're thinking about simple programs that sort of exist if you just start enumerating programs and seeing what sort of the simplest possible ones are and what they do. So this is an example of an extremely simple program. It's a cellular automaton. It consists just of a line of cells. Each cell is either black or white, and then at each step, the color of each cell is determined by a rule that in this particular case just says, look at the cell immediately above me and immediately above me to my left and right, and if any one of those cells is black, make the cell itself be black on the next step. So you start off from one black cell, and that's the pattern of behavior that you get. Now, if you go on a little bit longer, you can kind of see that behavior here, and you can represent that rule, essentially the program that's being run here, by that little icon at the bottom there. And so simple rule, simple program, starting off from just one black cell, you get a simple pattern of behavior. So you might think, well, that must always be what happens. Let's try some other rules. So here's another possible rule for what happens here. Now we've changed one bit in the program, And now instead of just getting a uniform black pattern, we get a checkerboard. Okay, well, let's go on. Let's change another bit in the program. Here's what we get in this case. You start off from one black cell, and you get this kind of nested pattern. Actually, you can understand this particular case in terms of sort of traditional math. This is basically binomial coefficients mod 2, if you figure out what's going on in the rules there. And if you let it run for a bit longer, you'll make this nice, very intricate, but nevertheless very regular nested pattern. So at this point, we might conclude that there's some theorem here that if the rule is simple enough, then the behavior must be somehow correspondingly simple. But that would not be true. And in fact, you can just do the experiment, which I did ages ago, and it's now kind of trivial to do with Mathematica, of just looking at all possible rules of the general type that we're dealing with here, black and white cells, nearest neighbors. Just ask what happens when you run each of those possible rules. You can represent the rules by some number that's just the decimal version of the binary bits for the different outcomes. And what you see is all sorts of different kinds of behavior. Most of the time what happens is pretty simple, but sometimes something more complicated happens. And my all-time favorite example is this rule 30. And if we run that one a little bit longer, here's what it does. So we start off from just one black cell. We run that rule at the bottom there, and we get this kind of slightly complicated looking pattern. If we run it for a bit longer, this is what it does. And you see there's some regularity over on the left. But for many purposes, this looks pretty complicated and quite random, actually. And for example, if you look at the center column of cells in this particular system, for all practical purposes, that center column of cells seems to be completely random. And in fact, it's random enough that we used it as a pseudorandom generator in Mathematica for many years. It's just being retired now because we found a slightly more efficient way to do this. But another cellular automaton. So even though the rule is really simple, the behavior that it generates is sufficiently complicated that, for example, for practical purposes, it seems completely random. So the question is, so that's an interesting thing. It's kind of not what one's traditional intuition from things like engineering would sort of tell one should happen. One would think that if one wants to make something as complicated as this, one would have to go to lots of effort to do it. And similarly, in natural science, if you see something as complicated as this in some system in nature, you might reasonably conclude the rules that make it must be really complicated. It must have gone through endless eons of biological evolution, natural selection, or it must have somehow had some very elaborate setup to be able to produce it. And in fact, it's a general feature of the natural world that it's full of stuff that looks very complicated, and it sort of seems, it's kind of an embarrassment of modern technology that if you're shown two objects and you're told one of them is an artifact, one of them is a natural object, a good heuristic for deciding which one is the natural object is it's the one that looks more complicated, and the one that we've gone to all this effort and technology to produce will be the one that looks simpler. But so, it seems like nature has some secret that lets it make complicated stuff in a kind of effortless way. And I think this Rule 30 thing has a lot to do with what that secret is. That if you just sort of go into this computational universe of possible programs, that it's actually remarkably easy to get things that seem to us very complicated. And you can go on and you just explore the space of possible programs. You can get nice things like this and so on that seem quite. Seem like this might be something that you see in some elaborate natural system, and you might imagine it came from some very complicated origin, but actually it's a very simple rule of the kind that I just mentioned. So you can ask the question, how does this work in other kinds of? So this is a sort of basic phenomenon that if you just sort of go out into the computational universe, it's easy to find really complicated stuff out there. It's not stuff that, for the most part, is accessible to typical mathematics. We'll talk about that more in a little bit. I mean, for example, those nested patterns, you can represent those. Those are binomial coefficient mod 2 and so on. But there isn't some special function that we could put into Mathematica or something that would represent the outcome of a system like this. Well, the question you can ask is this some special phenomenon that has to do with cellular automata and discrete systems and all that kind of thing? You can look at Turing machines. There's a simple Turing machine. You find out that you start getting really complicated behavior in Turing machines quite quickly. You can go into the sort of heart of traditional mathematics. You can look at partial differential equations, for example. There are a few typical sort of textbook partial differential equations. You can then ask the question, if you just sort of search in the space of all possible partial differential equations, what kind of stuff is out there? And you pretty quickly, these are some, hopefully, let's see. Those are some simple nonlinear wave equations, which actually have been great tests for Mathematica's differential equation solving capabilities for years now. They're just things that you find if you start searching in the space of possible PDEs, and they're things where they look, the behavior, like Rule 30, looks really complicated. It's kind of hard to figure out actually for sure what this behavior is, because these are not PDEs that have any kind of exact analytical solution or anything. And if you try to run them with numerical differential equation solving capabilities, you discover that it gets progressively more difficult to do that. And in fact, if this was the place where you were looking for the sort of original phenomenon of simple rules doing complicated things, you would be continually worried that actually the results you were getting were the result of some glitch in the numerical analysis or something, and not sort of a real feature of the systems one studying. And that's one of the features of something like Rule 30. This is a completely deterministic system, and the bits just are what they are, and so there's no kind of question about what's going on. Well, so one of the things one can ask is, okay, we're seeing all this behavior. How can we sort of understand at a more fundamental level what's going on? I mean, why, for example, what's the fundamental reason that things like this look as complicated as they do? Well, it's a somewhat long story, but the principle that I think lets one understand a lot of this stuff is what I call the principle of computational equivalence. And basically the idea of it is, think about all these processes that we're seeing here as computations, and think about not only these processes, but also the processes that are going on in the natural world and in our brains and in the statistical analysis or mathematical analysis or whatever that we're doing. These can all be thought of as computational processes. And then the question is to sort of compare how sophisticated these different mathematical processes, the computational processes are. And you might have thought that things with really simple rules would correspond to really simple computational processes. Things with more complicated rules would correspond to more complicated computations. But this principle of computational equivalence says that that isn't in fact true, and that instead, once you are above some fairly low threshold of things not being sort of trivial in their behavior, then almost any system will actually be equivalent in the sophistication of computations that it performs. And so that principle sort of tells one that, well, if that's the case, then our brains looking at this thing and trying to analyze it can't sort of outrun the computations that are going on in this system itself. And that leads to this phenomenon they call computational irreducibility. So if you look at sort of traditional science, one of the big things that sort of everybody's proud of is that you can make predictions. You can say, you try to trace a planet going around an idealized star for a million, orbits or something. You don't have to actually follow all those million orbits to find out where the planet will be. You just have to plug the number 1,000,000 or something into some formula, and you can immediately figure out the result. You can effectively computationally reduce the effort that the planet went to figure out where it will go. So here we might ask the question, if we look at one black cell down at the bottom here, can we work out whether that's one cell down at the bottom, can we work out whether that cell will be black or white by some procedure that's much more efficient than just tracing through every step here? Well, this idea of computational, if that was the case, then we as the thing figuring out what color the cell is going to be have to be somehow computationally more sophisticated than this system. And the point of this idea of computational irreducibility is that that won't be the case in something like this, and that therefore the only way to work out what will happen is effectively just to simulate each step. Well, so this principle of computational equivalence has all kinds of predictions about things. So one of its predictions is that if you look at these systems, that there should be that these systems should be, for example, computation universal. So that means that with an appropriate initial condition, for example, it should be possible to program the system to behave like any other system. That's kind of the feature of that's the sort of the big discovery of the 1930s, that computation universality was possible, and that it's possible to have sort of a single piece of hardware, a single underlying rule that can be programmed by changing its initial conditions to emulate any other system of that type. So, for example, it's kind of fun when you have a mathematical type principle that for which you can start to get sort of evidence in a kind of more natural science type way. So, for example, and in fact, you can then ask whether it's true that these simple systems show computation universality. We don't yet know about Rule 30. I'm afraid it's going to be somewhat hard to figure that out. But we do know about this one. This is Rule 110. This is starting it from random initial conditions. You can see it has these little structures that run around that look like they might be I don't know, elementary excitations in condensed matter physics or particles in particle physics or something. But anyway, or they might look like there's some kind of logic elements that are interacting with other elements and so on. Anyway, one can prove that this particular creature is capable of universal computation, that there exist initial conditions that you can set up that will make this emulate any other Turing machine or anything like that. We also actually know for Turing machines, I've been curious what the simplest oh, I can't get to the network, can I? Humph. That's a shame. Oh well. Well, anyway, I've been curious what the simplest universal Turing machine would be, and it turns out I don't think I have. Oh yes, I do have a picture of it. Good. Okay, there we go. Enumerating possible Turing machines after about most simple Turing machines have very simple behavior. This is the first Turing machine that has not obviously simple behavior, and it's a Turing machine with just 2 possible states and 3 colors on its tape, and that's kind of what it does, kind of uncompressed. This is what it does if you just look at the steps where the head's gone further to the left or right than it's ever gone before, and you can see it looks a little bit like one of these cellular automaton patterns. But the question then is this principle of computational equivalence would say that this sort of first not obviously trivial Turing machine should actually be computation universal. And so a few years ago, in an effort to get this question answered, I sort of put up a prize for determining whether in fact this Turing machine was universal or not. And very nicely, after a fairly modest number of months, I thought this might be one of these questions that was open for a century or something, but it turned out after a modest number of months, a young English chap proved that in fact this thing is universal. So it's the simplest universal Turing machine, and it's a nice piece of evidence for this principle of computational equivalence that this thing turned out to be universal. Well, okay, so we have this kind of, we have these various sort of principles about how these things work. One question that one can ask is, how does this relate to mathematics? What's kind of interesting about the sort of enumeration of possible programs is that we can kind of take that sort of approach. We could, for example, take it in mathematics. I mean, if you look at, well, okay, so here's a version of mathematics. This is basically writing out all the common axiom systems that are used in mathematics today, plus some even slightly obscure ones. It's not you can fit the axiom systems in a small space. It's kind of like a simple set of rules, and from these simple rules, there are about 3 million theorems that have been published in the literature of mathematics that have been proved essentially from these axioms. People don't necessarily always know exactly what axioms they're using, but some approximation to that. So you can ask the question, you can ask all kinds of questions. For example, you can ask, let's imagine looking at sort of the space of all possible axiom systems, just like we're looking at the space of all possible programs and so on. What do things look like in the space of all possible axiom systems? So this is a kind of an ultimately desiccated version of mathematics, where these are axiom systems going down the left and theorems going across the top. And when a particular theorem is true in a particular axiom system, there's a black dot, and when it isn't true, it's white dot. So each one of the rows in this diagram is effectively a field of mathematics. One question that you might ask is, where do the fields of mathematics that people know about right now, where do they lie in this sort of space of possible fields of mathematics? So I was interested in that question a number of years ago, and so for example, one area where you can look at that is in Boolean algebra. Let's see, I think this is the right thing. Yeah, there we go. So if you look up the axioms of Boolean algebra in a standard textbook, you'll find something a bit like this. And if you were to say, well, where does that axiom system lie in the enumeration of possible axiom systems? It's pretty far out there. But that isn't the simplest possible axiom system for Boolean algebra. So for example, that has and or and not in it. We known for 100 years that you can get Boolean algebra by just using the single NaN Sheffer-Stroke operation. And then there were axioms found a long time ago for Boolean algebra using just that single NAND operation. But actually, you can ask the question, what happens if you just sort of search the universe of possible axiom systems? How long does it take you before you find an axiom system that actually is Boolean algebra? So I did that, and it turns out after about 50,000 axiom systems, you find this axiom system here, which is a single axiom with 6 NAND operations in it. And it turns out that axiom system is actually Boolean algebra, and you can prove that. There you go. There's the the proof that that axiom system is actually Boolean algebra. It's an automatically generated proof. These days you can actually do this in Mathematica. It takes a few seconds to prove that that axiom system reproduces the standard axioms of Boolean algebra. So it's sort of interesting that in the space of all possible axiom systems, about the 50,000th one is Boolean algebra. Commutative group theory is, it depends how you enumerate the axioms, but if you use some simple lexicographic kind of ordering, it's about the 50,000th is Boolean algebra, maybe about the 100,000th is commutative group theory, and then you keep going from there. There are many technical details. So if you say, where's Peano arithmetic, for example, these are pure equational logic axiom systems, not axiom schemas, so you don't actually get Peano arithmetic in this enumeration and so on. But it gives you some indication of what's going on, that in this sort of space of possible axiom systems, one has, that's where these things lie. So you can ask questions about, well, what about all the other mathematicses that were left behind, so to speak, all the other all the other kind of rows in that diagram that I had, and why did we pick the particular mathematicses that we did here, and what kinds of things, what are all the other ones about? And people sometimes say, well, so in a sense, when we look at sort of models of the natural world that we get by sort of just looking at what's out there in the computational universe, we're picking things that aren't the traditional mathematical models, traditional mathematical equations, traditional axiom systems, and so on. And we're finding out that often those things that are sort of out there in the computational universe are actually good models for things in our actual natural universe. And people sometimes say the reason that the mathematics that we have is the way it is because that's what we need to describe the natural world. I think that's just not true. So one might ask the question, why have we ended up with studying just the particular axiom systems that we've ended up studying? My main conclusion about that is that it's sort of a historical thing. I mean, it started off, mathematics started off with arithmetic and geometry and things in ancient Babylon, and then people have had these particular methods of generalization that have been used ever since that have led to particular kinds of things being studied. Now, I think another big issue is when you start studying questions about things like cellular automata and these kinds of all these kinds of systems in the computational universe, one of the things that you run into quickly is things like undecidability. So this phenomenon of computational irreducibility that I mentioned before is kind of a junior version of undecidability. If you ask the question, what will ultimately happen in one of these kinds of systems, the answer to that question will tend to be something that that can be undecidable. And so when you start looking at these systems just these sort of random systems that you pick in the computational universe, lots of questions about those systems turn out to be undecidable. Well, mathematics and all those 3 million theorems that have been proved in mathematics, those are examples of things that didn't turn out to be undecidable. They turned out to be provable by humans even. I think that, so one question is, why isn't there more sort of undecidability in practical mathematics? Why doesn't one run into it more often? I mean, if you look at Gödel's theorem, for example, which was sort of the first example of this, it seems like a put-up job because Gödel's theorem is proving, is showing that this statement is unprovable. Well, the big achievement of Gödel's theorem was showing that this statement is unprovable could be encoded in Peano arithmetic. And that in effect that was sort of the first piece of software engineering or something, was to show that using Peano arithmetic you could build a program that was essentially the question, this statement is unprovable. But that seems like kind of a put-up job and not a sort of natural thing that would occur in mathematics. Yet, sort of in this computational universe, it's really common to find undecidable stuff. So the question is, why doesn't that show up more often in mathematics? And I think the main answer is because mathematics, like most fields of science, is set up to basically examine those things which its methods let one make progress on. So, for example, if one looks at what's been studied in, let's say, physics, there are lots of systems that exist in the physical world that physics hasn't said very much about, let's say, fluid turbulence, things like this. Lots of examples of this. And if you sort of unravel it, it seems that what's going on is that physics tends to define itself to be about those systems where the methods that have been successful in physics, which are typically things about differential equations and so on, have been successful. And so similarly in mathematics, I think what sort of happened is that mathematics has navigated through these kind of narrow paths in which you don't run into kind of rampant undecidability all over the place. If you just start asking kind of math questions at random, it's not difficult to run into all kinds of undecidability. Let's see, maybe I have an example of that. If you look at, well, gosh, you can, well, here's a fun thing, actually. This is so you can kind of think about how the structure of mathematics as it exists today, what it's like. This is just a plot of the theorems in Euclid and their interdependence. And this is a case where essentially one's starting from some set of axioms and then one's proving what one can prove from those axioms. And this is not an uncommon way, in effect, for things to work. I think the question that so sort of a question is when oh, here's an example. Here we go. So this is kind of a fun case. This is looking at the proof lengths for different propositions in Boolean algebra. For various different axiom systems for Boolean algebra. So the different propositions this is sort of how hard is math type, how hard are these things to prove. This is different propositions along the bottom here, and this is the height is just how difficult different things are to prove. And actually it's sort of interesting that that those axiom systems, that the axiom system that I was showing, that's the minimal axiom system for Boolean algebra, it takes about 100 steps to prove the commutativity of the NAND operation. But once you have that, it actually isn't a particularly inefficient axiom system for doing these things. Well, in any case, one of the things that one could think about is, okay, if one's going to think about sort of how does one extend mathematics in the future and so on, there's a question of what will happen? Will it be the case that mathematics sort of runs into this sort of hopeless wall of undecidability or not? And you could take an example like, I don't know, Diophantine equations, where you can ask the question: what's the kind of historical progression of success in solving things like that? So linear Diophantine equations, they were figured out by Diophantus in 100 AD or something. Quadratic ones figured out by Gauss around 1800. Then we got the elliptic ones that were figured out roughly 100 years ago now. And the question is, as we go forward, we know that eventually there will be Diophantine equations that where the question of whether they're solvable or not is undecidable and so on. But the question is, will that happen soon? Will that happen in sort of relevant areas of mathematics, or is that far away? Will it be the case that sort of every century we crack another level of possible Diophantine equations? My guess is that, and it relates to this principle of computational equivalence, that actually the wall of things that are effectively undecidable and so on is close at hand, and the only reason one hasn't seen it is because the methods that one's tended to use to explore mathematics have avoided it. I mean, a typical thing is that when one generalizes things in mathematics, I think the most common approach is to say, well, let's take a theorem that we really like unique factorization or something, and let's look at the largest class of things that still satisfy this theorem, and that's how we kind of generalize from one thing to another. As opposed to just saying, let's look at the universe of all possible axiom systems or something and just sort of enumerate those at random. Well, so there's lots of things that then become, if you sort of imagine that you're going to run into things like undecidability and so on quickly, then it gives you sort of a different methodological point of view about how one should sort of make progress in mathematics, and the fact that one should try and do experiments in mathematics rather than trying to specifically set oneself up to prove theorems and so on. And I think that's something that with Mathematica in particular, that's been something that becomes very possible to do, to just sort of explore experimentally what happens in different mathematical systems. And I'm going to try doing something here. I'm going to see if I can finally get this network to work, because I really want to show you some stuff here. Aha, I thought that might work. If I disconnect the other thing, this works. Okay, so there's a question of what, let's see whether this now works. Oh, very, very good. Back to, so I mean, hopefully we can, if we type in something like this, hopefully it will be able to compute that. Actually, it's kind of interesting what I mean, sort of the and this will come back to sort of the questions about what mathematics should be about and so on. But oh my gosh, what just happened there? Oh no. Now how could that happen? It's back. Okay, even more mysterious. Okay, so what we're trying to do here is to answer. We've given some question here. We're trying to sort of generate a report on interesting things that can be said about the answer to that question. So, there's some plots of the integral, and there's some alternate forms of the integral, and there's some definite integrals that it thinks might be interesting. We can ask it to sort of show the steps that could be taken to work out this integral. These steps have absolutely nothing to do with the way that Wolfram Alpha and Mathematica underneath it actually work out these integrals. They do it in a Mathematica works out integrals in this incredibly industrial way using generalized hypergeometric functions and so on. This is sort of a fake derivation that's useful for humans trying to understand how you might do this. The kind of thing that we're in Wolfram Alpha, we're sort of trying to collect knowledge, computable knowledge about all kinds of things. There's some sort of basic information about some knot. We could ask some basic information, what is the population of Oxford? How about that? Hopefully it'll figure out that, university, okay, so if it guessed that, 18,000 people, let's say, what does it think if it's a city instead? Okay, 154,000 people. Or we could ask it something like, we could type in some sequence like this, it'll probably figure out that that's a genome sequence, and it'll go and look on the human genome and tell us where there are matches for that particular thing. Or we could ask it all kinds of stuff. How about something like this? We could ask it something like that, or we could say, it will show us where the ISS is right now. It's an interesting case of sort of a combination of a feed of actual data from the world with computation about solving the differential equations to work out where the thing will be. Or we could, for example, we could ask it all kinds of things. We could ask it about I don't know. How about we ask it about cell phones? There's lots of things one can compute in the world. So let's see whether this. There we go. So this is telling us about. Let's ask it to do more here. It'll compute all sorts of things about the distribution of prices of cell phones and so on. I think you can ask it. What is the? How about let's ask it. Banana consumption in France, let's say, it'll probably be able to tell us something about that. Oh wow, that's interesting. Something obviously happened there. It's gradually recovering, but anyway, the point in Wolfram Alpha is to kind of do the thing that is to sort of collect as much knowledge as possible and make it computable so that one can actually get specific questions answered. Okay, how does this relate? So a lot of that is not about mathematics. A lot of the knowledge that's out there in the world has absolutely nothing to do with mathematics. I mean, there are all these different kinds of areas that we try to cover in Wolfram Alpha, and we're gradually covering more and more stuff. And you can do things in Wolfram Alpha. You can say. You could not only deal with data that it already knows about, you could also, for example, upload an image, let's say, and it'll go and use the image processing capabilities that Mathematica has underneath to go and process that image, or you could ask it questions about that image. Hopefully, there we go. And it's telling us what the dominant colors in the image are and things like this, and we could go ahead and make this interactive, and it'll now use our computable document format that's based on Mathematica to make this something that we can sort of interactively do things with. And you can also upload blobs of data that you got from somewhere. So you could upload a database or a spreadsheet or something, and then what Wolfram Alpha will do is to try to figure out what it can say that's interesting based on that data. So here's some a bunch of data, and if it wakes up here, it'll try and tell us interesting things about that data. It'll plot it. It'll work out probably some statistical kinds of computations based on this data and try and come to various statistical conclusions about it. Let's see if it does that. Okay, there we go. So somewhere down here, it's telling us that various groups differ, and it's coming to various conclusions based on statistics of this data. Okay, so how does any of this relate to things in mathematics? Well, one of the things that I've sort of been curious about is Mathematica has a definite model of how sort of mathematical computation should work. It's something where you give it an input, it will generate an output, and that's that's the mode of interaction. But one of the things that people say, people will come and talk to us and say, I'm a pure mathematician and I can't use Mathematica because I don't compute anything. I don't think that's entirely correct. I think that it's still the case that sort of the pieces of what happens in pure mathematics are computations. But what's the thing that I realized recently, I've been sort of curious about these different models of sort of mechanizing mathematics. I mean, there was back in the history of mathematics, in 1900 or so, people like Hilbert was saying, gosh, we can turn mathematics into this purely mechanical process that, people were saying was like, I think there was not everybody liked the idea that mathematics could be turned into a mechanical process, but that whole program got sort of thrown off track by Undecidability and Gödel's theorem and things like that. But still, we can imagine that there's sort of a systematization of mathematics that can be done, and there are various models of systematization, like the Whitehead-Russell, Principia Mathematica. Kind of the idea was, let's systematize mathematics by representing the process of proving things and so on. Well, that particular approach to systematizing kind of the doing of mathematics didn't turn out to be all that fruitful. A much more fruitful approach turned out to be this computational approach of saying, give inputs, compute, generate an output, which in a sense is a more kind of 19th century type approach to mathematics. So the question is, with the sort of 20th century Bourbaki, etc. types of mathematics, how might one start to automate things like that? And I guess my sort of amateur from the outside version of what that kind of mathematics consists of is that every paper starts with something like, let F be a field with such and such properties and so on. It's very much describing a structure rather than rather than saying, here's the input, compute the output. So the question is, how can one sort of think about automating in mathematics where one's thinking about describe the structure and go from there. So I finally realized recently that Wolfram Alpha actually gives us a way to think about that, because if I type in something like I don't know, if I type in carbon dioxide or something, I'm not asking a question. I'm not oops, I misspelled it too, but I figured it out. I'm just saying, what do you know that's interesting about carbon dioxide? And so similarly, one can imagine you state something about some mathematical structure and say, what do you know that's interesting about this mathematical structure? So one thing you can imagine doing is just automatically proving theorems about that structure. And so one problem with that is, well, you can go and you can start proving theorems, and you can generate all these theorems, but most of these theorems are completely uninteresting. So one question is, can you automate the question of which theorems are interesting? And I actually thought that would be, that if you ask, let's say in Boolean Algebra, you say there are an infinite number of possible theorems, which of those theorems are interesting? So a practical definition of interesting might be, it's given a name in a logic textbook. And there are about 14 or 15 theorems that are given names in typical logic textbooks. And you can ask the question, is there something special about those theorems? Or are they just purely historical? Is which ones were given names just a purely historical thing? Well, I assumed that it was purely historical. To my surprise, it is not. And for example, what you can do, if you just sort all the true theorems of Boolean algebra in some kind of simple order of, some simple order of sort of number of symbols and some kind of lexicographic order, and then you ask the question, you just keep going through this list of true theorems of Boolean algebra, and you say for each theorem, you say, can it be proved from theorems that are earlier in the list? Okay, so there are a certain set of theorems that cannot be proved from ones that precede them in the list. And in effect, those theorems that can't be proved from ones that precede them in the list, those are the simplest statements of sort of new information about Boolean algebra. As you go on further in the list, you'll get sort of hairier and hairier versions of those. But each one is the sort of the surprise as you go through the list. Well, it turns out that the ones that are sort of the surprises as you go through the list are, with one minor exception, precisely those ones that are the ones that are given names in logic textbooks. So it's sort of interesting. This is a way one can automate this kind of notion of what's interesting in the set of possible theorems. And you can imagine in general, for mathematics, you can imagine some network of all theorems and so on, and you can ask questions about, there are terms that one uses in mathematics, a powerful theorem, a surprising lemma, all these kinds of things. And so the question is there some graph theoretical way of understanding what does it mean that it's a powerful theorem? Does it mean that there are big blobs of theorems over here and other big blobs over here, and then there's this surprising connection between them? What does it mean to say that it's a powerful theorem? There are probably sort of ways that one can take what we think of as sort of the intuition of how mathematics works and turn that into something that's automatable. But anyway, the thing that so the question is, given this sort of approach to mathematics where you're describing a structure and you're saying what's true and interesting about the structure, that's one can imagine doing some automation of that, and we've sort of started trying to do experiments on this kind of thing. The other thing one can imagine doing is taking the 3 million theorems that have been proved in the literature of mathematics and curating those, just like we curate properties of chemicals, features of popular music, all kinds of medical diseases, things like this. Curate all those kinds of things. So why not curate the theorems of mathematics? So we've actually started a little pilot project to do that. It's not clear how hard it is. It's not clear, it's not clear how many mathematician years it will take to do this. It's also not completely clear how you want to represent the results. The particular area that we happen to have picked to do sort of a pilot project is a slightly obscure area, but it's a nice, well-defined area, which is continued fractions, which have a long history, goes back a long way. You can get the complete literature of continued fractions, and it's a modest number of papers, and it touches various different areas of mathematics. It's not, in and of itself, it's not a particularly exciting thing to be curating, but it's a useful kind of proof of concept for what one can do. So we started doing this fairly recently, and already actually there'll be things showing up in Wolfram Alpha fairly soon, where you can start asking it about sort of theorems about continued fractions, and you can say, given that I have this continued fraction, what theorems have been proved that are, that relate to the convergence of this kind of continued fraction or something like that. And because these theorems are represented in a computable way, it's possible to just derive, to automatically figure out which theorems are relevant and so on. And actually, it's sort of interesting, just in the process of doing that, just the process of systematizing, the folks who were working on that realized, gosh, we can systematize even further, and we can prove some much more powerful theorems about these things and much generalize what was there, which was kind of a fun thing to realize, that just the very act of trying to organize these things in a way that was systematically computable let one actually make sort of humans make progress too. Well, anyway, so I'm kind of, this is one of the things that if we look at sort of what's mathematics supposed to be like in the future, one of the things that I suppose that way back when, before Mathematica, there was such a time that people like me at least remember, any piece of mathematics, any computation you had to do, likelihood was you were going to have to work it out by hand, and you were going to have to learn how to do those integrals by hand and all those kinds of things. We've now been able to automate that type of thing. We've sort of systematically started to automate being able to sort of deal with mathematical facts and just knowing things about knots or things about particular differential equations, those sorts of things. The thing that I think if we succeed in this effort to sort of curate all the theorems of mathematics and set things up so that it's possible to sort of automatically generate the interesting theorems about something, then the likelihood is that sort of the future mathematical process will involve kind of, you figured out this thing, it's kind of interesting, I wonder what's true about it. Within a few seconds, you'll get some big list of theorems that are true about this particular thing. So that's sort of the traditional approach to mathematics. That's kind of the potential future of that. I kind of tend to think that there's a vast sort of ocean of unexplored sort of generalization of mathematics that exists in this kind of computational universe of possible systems. I think for the most part, it's typical of the progress of science that when things need to be studied in a way that is methodologically different from what's been done before, what gets built is sort of a new science. It could have been the case that these sort of systems that, these computational systems were studied as part of, quotes, mathematics. I doubt that that will be the case because mathematics, has chosen its particular approach to doing things, and that approach is not so valuable in the case of these more general computational systems. But there's sort of this separate branch of the generalized mathematics that you can start to build. One feature of that generalized mathematics is that the primary methodology tends to be experimental at first, and from the experiments then deducing more general principles and going from that in the way that lots of areas of science have tended to progress. And I think that's another feature that I suspect that there is a sort of the generalized mathematics, at least if not mathematics itself, like every other area of science, will eventually be more experimental than theoretical. But in any case, I kind of find it interesting that I happen to have spent lots of time thinking about sort of generalizations of mathematics and ways in which the current sort of approach to science based on mathematics kind of doesn't give one the whole story. It's a little bit strange that we now get involved in kind of building the sort of Noah's Ark of existing mathematics and trying to sort of preserve the collection of theorems and so on that exist in existing mathematics. I kind of think of it, I don't consider it sort of the necessary thing that all this mathematics that's been done is sort of the only mathematics that could be done. Rather, I consider it much like a cultural artifact. It's kind of, in fact, I would even argue that one could say that sort of this network of all these theorems in mathematics is the single largest artifact that's been built by our species. With more hands having touched this thing, putting together these theorems, it's the largest sort of coherent artifact that's been built. And so it seems like an interesting thing to try to preserve and to try to automate sort of access to. Well, I should probably stop there. I've probably gone way over time anyway, but I'm more interested to hear what people have to say, questions, comments, and so on. So thank you.